Hi all. So today we're going to talk about this problem 2.26. So it asks us about this chain with mass m hanging between two walls, and the ends are the same height, and with theta, the angle the rope makes with each wall. And now we're trying to find the tension in the chain at the lowest point. So if we look at this diagram here, this is like half of the rope, like this part. So then the tension at the bottom point will be this. This is the tension we're trying to find. Let's call it T prime. And then it's asking us to do this in two ways. First, by considering the force on half of the chain. So now let's look at this half of the chain. What forces does it experience? Well, first, it experiences a tension force at the bottom, right? Pulling right, directly horizontal. And then there's also this other force, between the wall and the rope that's pulling on the rope, and the rope itself has weight. And because this is half of the chain, the mass is basically half mg. And so now let's balance the forces. So the y direction we have, because this is theta, if you look at this triangle here, just imagine this is a straight line down here, and then this would be t. And so the y component would be t sine theta, and it must equal t cosine theta needs to be equal to half mg. And then for the x direction, t sine theta, this component here, needs to equal to t prime, which is pulling directly to the right horizontally. And so now we can try to solve for t prime. So from this equation, we know that t equals to mg over 2 cosine theta. And so t prime is equal to sine theta mg 2 cosine theta, which is half mg tangent theta. Just remember that tangent theta is sine theta over cosine theta. And so that is basically part A. For part B, it is asking us to use the result from problem 2.8 to find the tension in the chain at the lowest point. So basically the result of 2.8 was this formula we obtained, y of x. So if you haven't checked out this problem, that's okay, because we're just using the result. But if you're interested about in where this formula came from, go check out problem 2.8. It's really interesting. So we have this formula, y of x equals to 1 over alpha cos alpha x. So what does this formula tell us? This formula basically is the shape of that curve, of the curve of this chain hanging between two walls. And it is asking us to consider the vertical forces on an infinitesimal piece at the bottom. And then we'll have a tension in terms of alpha, and then find alpha in terms of theta. Okay, so let's consider a tiny piece at the bottom. And then let's do a force analysis. So then there's a tension pulling on the right, and tension pulling up left, and a gravity force. So basically what this means, what t dx and t0 means, is that if we look at this curve, or let's just look at half of the curve. If I call this x equals to 0, so if I just quickly draw an xy plane here, I call this x equals to 0. This, another short plane, this would be x equals to dx. Just remember that dx is not the length. dx is not the length of this piece of chain. dl is. Because technically this is still not the bottom yet. Here's the bottom, but then we extend a bit of dx here. So that basically means, I'll exaggerate a bit, but sort of like if this is this piece of chain we're studying, so like if this chain is this, then we're just basically saying like from here of x equals to 0 to here, x equals to dx. There's still a very, very tiny bit of y here. So technically dx is still not the length, only dl is. So now we have notation out of the way. So again, let's do a force analysis first. So in terms of x components, we know that tx dx needs to be equal to tx of 0, and ty dx needs to be equal to ty 0 plus g. So basically, if we look at t dx, if we zoom in, it's pointing upward left. So then it has an x component and a y component. And then for t0, because it's at the bottom, so this point corresponds to this point right at the bottom, it doesn't really have a vertical component. It's just pointing to right horizontally. But then just for clarity's sake, I still wrote it as tx0. But then now we know that ty0 is 0. So basically ty dx needs to equal to g. Okay. So what is g? G is basically the gravitational force of this piece of chain that the chain experiences. So what can we do? Well, we know the density is rho, and then this piece of chain, the length is dl. And then we just need to times it by g. This is basically dm times g. That's the gravity force. But how do we find dl? Well, first let's think about a unrelated problem. Let's think about this function here. Let's say just a random function. And we're trying to find the length between x and x plus dx. So here and here. The length of this chain, dx plus dx. So what can we do? So we can write dl as, so this part is dx, this part is dy. And so we know that it is dx squared plus dy squared. It's basically a right angle triangle because this dl would be so small that on a big curve, dl is basically just a straight line. So then what is dy? Let me erase this first. Well, dy, we can basically write it as f prime of x times dx. Why? Well, because what does f prime of x means? It means how much the y has changed in a unit of dx. So then the change in dy will obviously be this times dx. And also it cancels because dy dx times dx is just dy, right? So then now we have this. And just remember we have f prime of x, not f prime of x plus dx. So this x corresponds to here. And so dl is square root dx squared plus f prime x squared dx squared. And then we can factor out dx squared. So dl equals to square root dx squared bracket 1 plus f prime x squared. And then dx comes out, we have this dx square root 1 plus f prime of x or squared. So now this is the formula for the length of the chain between x and x plus dx. So now here we're trying to find the length of the chain between 0 and 0 plus dx. So then we just need to plug in the numbers. So then we know that here dl equals to, if you look at this formula, it will be dx times square root 1 plus f prime of 0 squared. And so then we can rewrite dm as rho dl. And so g is basically dmg. And so g is basically rho g square root 1 plus y prime of 0 squared dx. And so now let's just rewrite the formula here so it's cleaner. So we know t x dx needs to equal to tx of 0, and then ty dx needs to equal to g, which is rho g square root 1 plus y prime 0 squared dx. And now what is y prime of 0? Well, let's think about it. There are two ways of doing this. So what does y prime of 0 means? It means the slope of the bottom of the piece, this piece at the very bottom. So then the slope is just 0. But then we can also see another way. Remember, we have the formula y of x equals to 1 over alpha cosh alpha x from problem 2.6 here, 2.8 here. So then what is y prime of x? Y prime of x is basically hyperbolic sine alpha x. Because of chain rule, this alpha x becomes alpha and it cancels this part, and then hyperbolic cosine becomes hyperbolic sine. And so obviously y prime of 0 is hyperbolic sine 0, which is 0. So then basically this part becomes ty dx needs to equal to rho g dx. And so now we have a formula for the slope. Ty dx over tx dx needs to equal to rho g dx over tx 0. So if you think about it, let me draw all the diagram here again. So if we have this short piece over here, and then basically this is, or let's think about this, and then this is tx dx and ty dx. So the slope of this segment here is just ty dx over tx dx. But this is not really helping us, so we need another expression to equal this, so then we can actually find something. So what else is this equal to? Well, we said this is the slope, so it will make sense to let it equal to y prime of dx. And what is y prime of dx? What can we write it as? Well, it is y prime of 0 plus y double prime of 0 dx. We do this because we don't know what y prime of dx is. The only thing we know is y prime of 0 and y double prime of 0 dx. So what does this mean? So again, let's think about another problem, an unrelated problem. If we have some sort of curve, and here we have the slope, and then here's another slope. And we're trying to find this slope. So then we're trying to find this slope. So how do you do that? Well, we use the slope plus the change of the slope over here. So how much the slope changes over here plus the original slope, we get the slope of this part. So what measures how much a slope changes? The second derivative, right? And then how much is this? This is dx. So this length here is times dx. And so basically y prime of dx is y prime of 0 plus y double prime of 0 dx. This is really like the Euler method for approximations. So you can also search up if you're interested in learning. So now it's very easy to find y double prime of 0 too, because previously we said y of x is 1 over alpha cosh alpha x, and then y prime of x is hyperbolic sine alpha x, and then so then the double prime is basically alpha hyperbolic cosine alpha x. So then what is y double prime of 0? Y double prime of 0 is basically alpha hyperbolic cosine 0. Oh, sorry, it should be here. So then it should be 0 here, and then hyperbolic cosine of 0 is basically 1, so it's just alpha. And then previously you said y prime 0 is 0, so then this becomes 0 plus alpha dx equals to y prime of dx. So then y prime of dx needs to equal to alpha dx. And then we wanted this because we want to equal this thing to this thing here. So let's do that now. So we have ty dx equals to tx dx equals to this thing here, y prime dx. And then we can write it like tx of 0 equals to ty of 0 plus rho g dx. So just, this is basically writing the formula here. And then since, well, ty of 0 is just 0, we don't need to write it because just remember it's the bottom piece. It's just pointing straight to the right. So then there's no y component. This is basically 0. So then this basically is, and this is equal to alpha dx. So now we know rho g dx over tx of 0 equals to alpha dx. So now the dx cancels. That's great. And then now we have tx of 0 equals to rho g of alpha. And so this is basically the force that the bottom piece experiences. Because again, that bottom piece only experiences force directly to the right, which only has the dx component. So now our only job is to find alpha in terms of something that's already known, and as well as rho, something we already know. So how can we rewrite it? Well, obviously it's very hard to just write alpha straight away, so let's try to write rho, because we know it's easy to write rho in terms of something else. And hopefully it cancels the alpha. Okay, so what is rho? Rho is basically m over L. Here, the m refers to the mass of the whole chain, okay? And the length is the length of this whole chain. So then we use the formula, well, we know the length of the chain is 2 times 0 to d square root 1 plus y prime of x squared dx. So here basically this formula is just half the length of the half of a chain, how long half is, and then we times it by 2. So now it becomes a full chain. And so now we have, because we know y prime is hyperbolic sine alpha x, so then we also know that 1 plus hyperbolic sine of alpha x whole thing squared equals to hyperbolic cosine alpha x squared. So then this thing becomes from 0 to d times 2 square root hyperbolic cosine alpha x squared dx. And so this becomes 2 from 0 to d hyperbolic cosine alpha x dx. And then this basically becomes 2 sine hyperbolic sine alpha x over alpha, and then x equals to d, x equals to 0. And because we know that hyperbolic sine of 0 is just 0, so we know that it's basically 2 hyperbolic sine alpha d over alpha. And so that is L. And then recall that rho is m over L. It's basically it's basically m over this thing here, so 2 sine alpha d over alpha, which is m alpha over 2 sine alpha d. And that's great, so it cancels one of the alphas. So remember, tx0 is rho g over alpha, and then rho is m alpha, so then it's m alpha over 2 hyperbolic sine h, so then let's write it, 2 hyperbolic sine of alpha d times g times over alpha, so cancels. So then this becomes mg over 2 hyperbolic sine alpha d. And now let's think about it. What can we do with hyperbolic sine alpha d? So we know that, just again recall that we know y is 1 over alpha hyperbolic cosine alpha x. So y prime is 1 over alpha, it's hyperbolic sine of alpha x. So what does hyperbolic sine of alpha d means? Well, it means the slope at x equals to d. So then what is the slope at x equals to d? Well, again, I'll draw a diagram here. So let's think about half of the curve here. So remember what we said d as. We said d is basically how long this half of the string is on half of this chain is, like the exponent, how long this is. So then this expression means the slope at x equals to d, which is basically the slope at here, the very top. And so what else do we know about this? Well, we know that it's theta here, right? Because the problem told us here. And so what is that slope in terms of theta? If we think about it, let's just think about that very, very top piece. We have theta and then this. And so what do we know? Well, it's basically this rise over run. And what is rise? Rise is basically cosine theta, whatever this length is. We can call it anything. Let's just call it d capital L. And what about this here? What is dl sine theta? And dl cancels, and that's why it doesn't matter here. And what is this? This is basically cotangent theta. And then we also know that hyperbolic sine alpha d is also the slope of this segment. So then hyperbolic sine of alpha d must equal to cotangent theta, right? So now we basically have t of x of 0 is 2 cotangent theta, and then on the top we have mg. And so if we write it, and then, well, 1 over cotangent theta is just tangent theta. So then t of x of 0 is half mg tangent theta. And just remember again, that bottom piece, it only has the right horizontal tension force. The piece that experiences at 0, because that force is pointing right horizontally. And so that is our answer, half mg tangent theta. And it corresponds, and it's equal to the answer that we obtained in part A, just much slower and with much steps. Thank you for watching.